Welcome to the next video in the group theory series. In this video, we will introduce cyclic groups and subgroups. Here you can see a summary of what we will discuss in the video. To begin with, let's start by describing the most canonical example of a cyclic subgroup, which is the integers mod n for any integer n at least 2. These are always cyclic because we can start from 1, repeatedly add it to itself, and eventually make your way through the entire group. To take a concrete example, let's use zmod 4. To make our way through the group, we compute 1 plus 1, which is 2. This, by the way, will start at 1, so then we get 1 plus 1 is 2. Then we get 1 plus 2 is 3. Then 1 plus 3 is 0, remembering that we're computing this mod 4. And then 1 plus 0 is 1. And we've made our way back to the starting point, the number 1, and we have made a tour all the way through this group, which is to say every element of the group has shown up in the tour. Let's now give the official definition for cyclic subgroup. So for any group element little g in big G, define the cyclic subgroup generated by little g to be the set of all integer powers of little g. So that's this. We use the notation of angle brackets around little g to denote this set. And we say that little g generates the cyclic subgroup bracket G, right? So we're saying that little g generates this subgroup. So that's a cyclic subgroup. We say that a group is cyclic if it is a cyclic subgroup of itself. So what I mean by that is that the group H is a cyclic group if you can find some element which generates the entire group. Now, clearly, every cyclic subgroup is a subset. That is to say, we know that if G is any element, this cyclic subgroup generated by G is always a subset of G. That's clear, right? G being a group, it is closed under products. But not only do we want it to be a subset, we would in fact like to show that it is a subgroup. To show that it is a subgroup is a relatively straightforward process. The subgroup criterion makes this very quick. So recall, what is the subgroup criterion? It is the idea that if you are taking a subset of a known group, and indeed that's what we're doing, right? We have that this is obviously a subset. Of a known group, big G, we're assuming big G is a group. So the subgroup criterion says that if that's our situation and the subset is closed under division, then it is a subgroup. Closed under division, recall, is that you take any element. Now we can represent any element as g to the I for any integer I, and another element, we can call it g to the j, j an integer, inverse, right? So this is division, right? This is g to the I divided by g to the j. And if we can show that this is an element of the subset in question, in this case, the subgroup generated by little g, then we'll know it's a subgroup, right? So we need to show that this thing is in the subgroup generated by G. Okay, well, by our now somewhat familiar exponent laws, it's very quick and easy to demonstrate that this must be equal to G to the I minus J, right? So you'll just kind of put the -1 together with J and then add the exponents and you get this. Now this is an integer exponent of G, right? After all, I minus J, that is an integer. Therefore, by definition, this is contained within the cyclic subgroup generated by G. There we have it. It's a very quick proof that this is closed under division and therefore is a subgroup. Now, we've already seen that the integers mod n is a cyclic group. It's probably worth pointing out before moving on that, in fact, although it is generated by 1 always, it is also generated by n minus 1 always, which is perhaps a little bit like something that you might not have been expecting. So let's take, for instance, in the integers mod 4 again, I claim that if we did n minus 1, that's 3 in this example, that generates the whole group, meaning, again, that the group generated by that element is all of Z mod 4. Okay, to see this, we'll just do a brute force sort of tour through the group. So we know we can start at 3, then do 3 plus 3, right? We're adding it with itself, which gets us 6, but 6 is the same as 2 when we're taking this mod 4. Then 2 plus 3 is 1 mod 4. And then 3 plus 1 is 0 mod 4. And then 0 plus 3 gets us back to 3. And we've now made a complete tour through the subgroup. So we just saw that Z mod 4 is generated by 3. That's the point. So a group can have many generators, right? Z mod n is always generated by 1. It's also always generated by n minus 1, and sometimes by even more than that. But in any case, that's the point that I'm trying to make there. Okay. Let's note that if you pick any group at all and pick any element, of course, you always get a cyclic subgroup. If we pick the dihedral group on n vertices, by which I mean d sub 2n, then the subgroup generated by R is the subgroup of all rotations. If you pick a reflection, you can easily show, as I've somewhat indicated here, that for any reflection, if you product it with itself, you simply get back to the identity, and that should convince you that the only elements in the cyclic subgroup generated by this reflection are itself in the identity. Now, you may have noticed that we have two different definitions of the word order, one for groups and one for elements. It turns out that, in fact, they kind of mean the same thing. And what I'm getting at by saying this is that the order of an element is actually the order of a certain group. Namely, what we will prove here is that the order of an element is the order of the cyclic subgroup that it generates. Although this result is useful in a number of ways, one thing that it does is sort of organizes the concept of order, so we can always understand order to actually mean the order of some group. Anyways, on to the proof. We will prove this claim in two cases. First, when the order of little g is infinity, and then when it is finite. In the case where little g has infinite order, I claim that every integer power of g is distinct. While that is generally true for our current purposes, I'll restrict myself to the non-negative powers. If any two distinct non-negative integers result in equal powers, so what I mean by that, you can see here, right? So take distinct integers, I and j, without loss of generality, we assume that I is less than j, and they result in equal powers of g, right? So if we assume this for contradiction, then we can certainly move g to the I to the other side, so to speak. What that really means is multiplying by its inverse, g to the negative I. The left-hand side becomes the identity. The right-hand side, we can use our exponent laws and form g to the j minus I. But this then entails that the order of g is not infinity, because after all, we have some exponent, which g to that exponent is equal to the identity. So there is some number making it equal the identity. And so by our definitions of order, the order of g would not be infinite, contradicting our assumption. So we now know that all of these elements are distinct, and that is enough, right? Since they are all elements of the subgroup generated by G, then there's an infinity of elements in the subgroup generated by G, and we're done with that case. Next, in the finite order case, I claim that the subgroup generated by G is equal to this set, right, which is, in fact, all of the powers of G mod n, right? So this would be G to the 0, this is G to the 1, and so on. So these are all of the powers of G mod n. And so we're going to prove this equality by a mutual inclusion proof. Now, in fact, to see this direction of the subset, it's totally trivial, right? Because after all, the very definition of the subgroup generated by G is the set of all integer powers of G, and that's exactly what's on the left-hand side. So this direction of inclusion is just trivial. For the other direction of inclusion, this one, takes a little bit more work. But in fact, it's mostly done by the reduction of order theorem that I proved in a previous video, saying that for a finite order element of order n, every exponent of g has an equivalent representation in the exponents mod n. And therefore, we get the reverse inclusion. Okay, now that is not the end of the proof. One further thing, for all we know at this point, is that some two elements of this set might be equal, and if that were true, then we would have fewer than n elements. So we're going to show that that is not the case. And we're going to do it again, very similar to how we did it up here. We're going to assume that some two of these are equal. Again, right, I and j, I less than j. Rearrange it, kind of like we did last time. And now the upshot is a little similar to what it was before. This time we're going to say, well, there exists an integer positive integer exponent of g, which is equal to 1 and less than n, importantly, right? Because j is less than n, I is between 0 and n, and not equal to n, but in any case, the important thing is that it is pretty clear from this that j minus I would have to be less than n. And that means that we have an integer that clears g, and which is less than n, but that contradicts the very definition of n being the order of g. So that is not possible. And so we know that all of these elements are distinct. So we now know that this set contains precisely the n elements listed here, and therefore the order of the subgroup is equal to n, which is the assumed order of the element. So the proof is now complete, QED. Now, I'm going to prove that cyclic groups have this nice property that, commutativity often makes calculations and things that you do in a group easier, and every cyclic group has that property. The proof is super, super short. So we're going to take any two elements, g to the x, g to the y, x and y, any integers, and we're going to show that that becomes g to the y, g to the x. How are we going to do it? Well, exponent laws tell us that we can simply sum the exponents and get g to the x plus y. Now, we know that we can rearrange integers, right? This is just an integer fact that we could turn that into g to the y plus x. And then again, use our exponent law to sort of export that back out as g to the y, g to the x, and we're done. QED. Okay, final thing that I will prove here is that what we're going to analyze the order of a product of two elements in a, which have finite order. So if we assume that we have elements A and B in a group G, and they commute with each other, right? AB equals BA. And if they each have finite order, then under only these assumptions, we can already say that the order of the product divides the LCM taken for each order. So that's true in general, and in fact, right, so stated doesn't have a whole lot to do with cyclic groups. But the next part, where we follow up and say, if we further impose the condition that the groups generated by A and B individually share only the identity element, then this divisibility turns into an equality. So that's what we're going to claim and now prove. The first part of the proof, where we merely assume that the two elements commute with each other, is fairly straightforward, right? So we want to prove that the order of AB divides M. Well, this is going to almost entirely come from definitions and the fact that we proved earlier, which is that if an integer clears an element, then the order divides the integer. That's all said somewhat fast, so I'll talk in more detail about this. Okay, for ease of notation, let's say that M is the LCM for these individual orders of A and B. Since by definition, that makes it a common multiple, meaning that it is a multiple of the order of A, right? What does it mean to be a multiple of something? Well, it means that M equals the order of A times some integer. We'll call that integer X. Likewise, M is a multiple of the order of B, so we get another integer Y like that. It is very straightforward to show, based on the same sorts of things that we've been doing this whole time, that A to the M then comes out equal to 1, right? Simply express it as that multiple, regroup things using the exponent laws, and you get the result pretty quickly. Likewise for B. Now, at this stage, we can then use all of that information collected so far to use commutativity, right? Now is the point where commutativity kicks in when we take AB to the M, right? We're trying to show, again, that M clears AB. And because they commute with each other, then we can actually distribute the M to each one individually, and then they turn into 1. From that earlier result, we now know that the order of AB divides M because M clears AB. Okay, now let's further impose the assumption that the subgroups that each generates only shares the element 1, the identity. Now we're going to prove that under this assumption, M is equal to the order of AB. We're going to do this primarily by definition of the order, right? So we're going to show that M has the defining property of order. What is that property? That property is that when AB is raised to the power M, it is equal to 1, and there is no smaller power such that that holds. We already know that AB to the power M results in 1. We proved it above. So now all we have to do is show that no smaller one does the same thing. Well, what that kind of means is that if you took any other integer, we're going to call it k, which has this property, right? AB to the k is equal to 1. If you take this other integer k, M is less than or equal to k, right? That's what it is to be least, is that if you took any other one, it would have to be bigger. So that's what we're going to prove, right? We're going to assume that k is some integer that also clears the product AB. Now, if k clears AB, and we can split it up as we've already seen once before, then we can now move k, or right, we can multiply by a to the negative k and get that a to the negative k is b to the k. Well, a to the negative k is an element of the group generated by A, but it's also, because it is equal to b to the k, it's also in the group generated by B. There is only one element like that, which is the identity. So we now know that, in fact, a to the negative k equals 1. Well, that means that negative k clears A. If negative a clears A, sorry, if negative k clears A, then the order of A divides it. And A divides, or order of A divides negative k if and only if order of A divides k. Even more directly, we get that b to the k is 1, therefore k clears b, therefore order of b divides k. So we now have this. Now, by a very simple sort of demonstration from definitions, order of A dividing k is the same thing as k being a multiple of order of A, and likewise for order of B. So that makes k a common multiple of order of A, order of B. So k is a common multiple of order of A, order of B. Well, but M is the minimal, right? It is the least common multiple, and therefore, by minimality, M is less than or equal to k. That is precisely what we wanted to show, and therefore, we have that M satisfies the definition of the order of AB, and therefore, it is the order. Okay, there's the proof, QED. Before sort of signing off here, just a real quick application of this idea. Let's take, for instance, in S5, we've got the permutation 1, 2, 3, and also the permutation 4, 5. These are disjoint from each other. Therefore, they commute with each other. So we've satisfied that portion of the theorem, the assumptions of the theorem in this particular case. Moreover, you can look at the subgroup generated by each one, fairly simple direct calculation, and you'll see that the only thing they share is the identity element. So we also satisfy that condition of the theorem. Now, the order of the first one is 3. The order of the second one is 2. That has least common multiple 6. And now, if you want, you can directly confirm that, in fact, yep, everything comes out as it should. The order of their product is 6.